Good afternoon. I am Alice Reed, Program Chair of Society of Quantitative Analysis and Behavior, and I would like to thank you for coming. Society is very interested in offering this tutorial series to ease the transition into quantitative analysis for members of ABA. So we've selected 4 preeminent scholars to represent their work. The first scholar that I'd like to introduce is Dr. James MacDonall. Dr. James MacDonall, Jim, is a very good friend and an outstanding researcher. Jim received his bachelor's degree in psychology from Overbrook College in Atlanta. Then went to Boston University for his master's and PhD, studying under Gary Bergolius. Jim's been teaching at Fordham University since 1978, where he's been especially successful working with undergraduates in the experimental and quantitative analyses of choice behavior, pharmacology, and neuroscience. You'll find many of his articles with student co-authors in a wide variety of journals in behavior analysis and neuroscience, which indicates the breadth of his research interests. The purpose of Jim's tutorial is to help those who are interested in attempting quantitative analyses. Jim is ideally suited for this tutorial. First, because of his experience introducing quantitative analysis to undergraduates. And second, because of his recent research demonstrating limitations in the generalized matching law. As a result of these limitations, Jim has developed the alternative model of choice to describe performance of concurrent choice procedures. But if any of Jim's students from Fordham are listening, you can always get him to stop talking about quantitative analysis by mentioning the magic word, fly fishing. Jim's passion for fly fishing was his Achilles heel. Jim's own mathematical model, the alternative model of choice, can probably account for his own choice behavior. Option 1, teach about quantitative analysis. Or option 2, talk about fly fishing. You can guess which one wins. I hope you all welcome Dr. James MacDonall.
Thank you. Thank you for that very kind introduction. I guess we need to get started. All right, first, we always have to thank people. I first want to thank Bill Polya for inviting me. And there's an exclamation point because we'll see if I really want to thank Bill after I'm done with the talk, if I was worthy invited. But this all started, Bill and I were talking after the tutorials last year, and I said that I found them fascinating for 3 years. But I thought one thing was lacking in some sense. Excuse me? Okay. That's all right. And I said that although I found the tutorials really very interesting, none of the tutorials have been aimed at people who are really beginning to get started, who are new in the field. And if we really wanted to get more people involved, we really have to have some of the tutorials aimed at people who are just starting out. And maybe even haven't started out yet, but are thinking about it, and to try to entice them into moving into something that some people may feel strange and anxiety-provoking. So Bill said, that's a wonderful idea, why don't you do it? And here I am. I also want to thank Henry Marcusella. He was a graduate student with me and then on the faculty, still on the faculty at Boston University. And we've been good friends and fly fishing together quite a bit. And in fact, some of the research I'll be talking about, I actually conceptualized driving from New York up to Cape Cod to go fly fishing. A 5-hour drive, and for me that offers uninterrupted time to think. And I'll talk a little bit about that later. Charlie Lewis, on the psychometrician mathematical psychologist at Fordham, has been very generous with his time with a number of questions. There are many other colleagues and many reviewers both from JAB and NIH grant applications who have made very useful and helpful suggestions for me. And I guess part of the final message will be listen to your reviewers. You may not think they're right, but they probably are. And anyway, the outline, I want to talk a little bit about history. I talk about some very simple techniques. I hope that we can learn some lessons, at least lessons that are applicable to me. I hope there's some generality. I certainly don't pretend that what I'm going to say is applicable to everybody. But I hope people can get something that is relevant to them. I'll talk a little bit about techniques relevant to models of one independent variable. I'll talk about some lessons I learned that says we may need a different model. And I probably won't get time to get to those. I've timed this talk out a couple of times and never really get there. I left on this slide in case we do. And I'll have some brief conclusions. But just like if you're applying for an NIH or an NSF grant, the first thing they say is you have to have a good idea, and that's true when you do research, it's true when you do quantitative research. The problem is, how do you know you've got a good idea? You really don't know you've got a good idea, at least from my perspective, my experience, until 2, 3, 4, 5 years later after you've done some work and found out either it is a good idea or you sometimes find out, no, it is not a good idea. So I modified that. You have to at least have an idea, and you've got to start there. My long and winding road in some sense reflects my musical interests. I began, in fact, with an interest in stimulus control, and that was really where my heart is, and in some sense where my heart is today. I'll talk a little bit about what happened to get me involved in quantitative analyses. One thing I think that's important is I'm not afraid of math. I was an engineering student for 2 years. Math has always been of interest to me, and although I was an engineering student for 2 years, I was not a scholar at the time. So I would not ask, please do not quiz me on my calculus as an engineering student. But the point is, you don't necessarily need calculus. I haven't used that. I'm not saying that knowledge of lots of mathematics is not very helpful. But I think you can do some interesting quantitative work that's sticking with less sophisticated or advanced mathematics. If you need some additional math training, this is an excellent book. They authors talk about it as a program instruction book. It's not programmed as we would call it. I should also mention, I'm going to put this PowerPoint thing on my website at Fordham, so you don't need to copy down anything. Just listen and hopefully get some reasons to then log onto the website and download this presentation. Anyway, it's really not a program instruction book as we understand it. But it does require you to work through the problem is, in a sense, of learning by doing. And it's really a very good book. If you need a refresher, this will probably be a little bit slow because you laboriously have to go sequentially through. All right, my story began in 1972. Tony Nevin was coming to the U to give a talk, and he asked everybody to review Bernstein's article on the law of effect. And it's not one the law of effect, it's on the law of effect. In that article, he mentions, refers to this work that ultimately wasn't published, that on a concurrent VRBR schedule, you don't get matching. He says, in some sense, that you cannot get matching first. What happens is you get a preference for the smaller variable ratio schedule, whereas on VI schedules, you do get matching. You get a graded preference, whereas in VRs, you get a bullet preference, essentially one and done. When I read it, I realized that this it really depends on how you arrange the variable ratio schedules and how you arrange the variable interval schedules. And in some very technical sense, and you have to be a second-year graduate student finding out that Bernstein is wrong about something is really sort of ego-inflating, and it's not necessarily a good motivation to proceed. But it did say, well, I've got some kind of idea. I went to David Scotty, who was really the first faculty member I ran into, and told him my insight, so to speak. And his response was so what? And that, he meant it one way and I meant it another. I understood it differently. He meant it That's an interesting observation, but you need to think about it and find out the meaning, find out the importance of it. And I misunderstood it and thought he had thought through my insight and seen that it was unimportant and was telling me to ignore it. So, for better or for worse, that's what I did for a period of time. But even though he wasn't thrilled by it, it kept nagging at me that there was something there, but I didn't know what it was. Finally, after I was tenured, I had a meeting with the chairman, and he said something very interesting, which is essentially that you have tenure. Instead of doing research projects that are immediate payoff, it's an opportunity to spend time engaging on a project that has lower probability of payoff, but also a project that, if it does pay off, has much greater significance. And I thought, oh, I never thought about it that way. That was a very interesting piece of advice. And I thought, well, I've always wondered about this stuff about Bernstein and variable ratio schedules. And let me begin to look at that and think about it. And so I did. And so I did a study. Rats, and tell you how long ago it was a PDA computer with SQAB. Some of you probably had those or know those. And the key in my insight, so to speak, depends on how you program the concurrent VRVR. The way Bernstein did, and certainly the natural way to do it, is have the left lever presses, or keypacks in this case, count a left ratio counter, and have the right keypacks count a right ratio counter. And what he finds is exclusive preference for the smaller VR. It occurred to me that that's not how things are done on a variable interval schedule. On a variable interval schedule, when the animal's at the left alternative, the left VI timer is operating, and the right VI timer is operating. So the time that the left lever is really incrementing both of these timers. When the animal's at the right lever, again, time is incrementing both timers. But that's not how the VR schedules work. So I thought, well, why don't we just have left lever presses increment the left lever and the right lever, and when a VR counter primes a reinforcer, if it's at the alternative the rat's pressing, it's delivered immediately. If it's at the other alternative, it's held until the animal switches and obtains the reinforcer. So it's essentially arranging the contingencies on a concurrent VR like the concurrent VR. And lo and behold, when you do that, you get a very nice rate of action. And I was powerfully reinforced. My insight, in fact, was correct. Not my insight about Bernstein being wrong, but insight in terms of the analysis of the contingencies. I then went on and did a number of experiments that went down dead ends, and I was sort of not stuck, but doing different things. I hadn't conceptualized it fully. And Larry Carlo was a new hire at Fordham, and he had also done some research in choice. And he sort of pointed out to me that you can really think about the contingencies in concurrent schedules, and that there's not just two schedules, but when the animal's at the left alternative, the VI timer at the left arranges reinforcers for staying left. The VI timer at the right is operating, and that schedule arranges reinforcers for switching right. Similarly, when the animal's at the right alternative, that timer now functions to reinforce staying at the right, and the other timer now functions to reinforce switching. And this, once it took me a while to get it. And once I did it, it was very interesting because, in some sense, concurrent schedules you conceptualize as having two independent variables, two schedules. Well, now there's four of them. And so that meant to me, you've got to find something new. I mean, here you can make manipulations that nobody else has done before, and that should produce something new and something that I hope would be interesting. Just because it's new doesn't mean that it's going to be interesting. So we first fiddled just with schedule values, and we saw that we could push choice or push preference around, but we were doing it in a highly non-systematic way. Nonetheless, we knew that it seemed at least that this manipulation was useful. But we also became clear that having four schedules operating at the same time to try to understand what was going on was simply too complicated. We had to make things simple. So I also knew the benefits of doing parametric research, so we decided what we're going to do is just hold two schedules constant, get them out of our analysis analysis in some sense. And we figured to really get them out of the analysis, let's hold them in extinction. And then we'll vary the other two scheduled values in a systematic way. We made the very bad choice in retrospect. We held made the schedules for staying in each alternative extinction and varied or began to vary the switch schedules, and all that produced was switching back and forth and really a very boring result. And so that didn't work. But the idea of holding two constants remained, and then we said, well, let's hold the stay and switch schedule, one alternative constant at extinction, take it out of the picture, and then just look at the stay and switch schedule with the others. And I did a study using variable ratio schedules. I was interested in some sense promoting the idea that in fact you can do choice exertion with schedules. And so we simply have here a little cartoon. The left lever presses incremented 2 VR counters, in this case a VR10 and a VR40. When the 10th arranged reinforcer, it was delivered immediately. When the animal switched to the right, if a reinforcer was arranged, it was delivered. If it wasn't, further presses, it wasn't delivered. And then further presses at the right lever do nothing. It's sort of a behavioral suspended animation. Nothing occurs until the animal comes back and presses the left lever, and then once again, the counter begins to increment. And we did a nice parametric study. I used all the combinations of the 10, 20, 40, and 80 for both staying and switching. So we had 16 conditions, and I ran them in various orders, and I got them the whole thing. And just before going up to Cape Cod, I plotted the results. And I was just astonished at the results I got. Here we have 16 conditions in a very orderly arrangement. And that, to me, was quite satisfying. And to just talk through it a little bit, here we're talking, this is the value of the schedule that reinforces staying, and this is the value of the schedule that reinforces switching. And so VR10 is the richest schedule for staying, and the VR80 is the leanest schedule for switching. So notice we get rich stay and lean switch. We get a very, very long run length. Run length is the number of responses in the left alternative divided by the number of switches to the right alternative. And you can just see that you get the shortest run length here, which is when staying is least reinforced and switching is most frequently reinforced. And in a very orderly way, a couple of little minor reversals, but in 4 rats, I was delighted. The empty cells here, it turns out that in some conditions, some rats would respond. It's simply VR schedules. If this was a VR80, one of these is a VR80, VR80, and that just didn't maintain the animal's behavior. In other cases, on the stays of VR10, right over here, the animals just never switched. They just stayed on that level of VR10, and they were happy with that, so I didn't have to drop those out. But I was very happy with this. But now I have a problem. I'm not trained in mathematical modeling. As I said, I got a reasonable mathematical background. I never took a course in graduate school, didn't know anything about it. And so the idea of trying to develop a model with 2 independent variables was beyond daunting. It was something I just couldn't conceive doing. And so I was driving up to Cape Cod. And the obvious thing is, well, you've got to somehow combine these in a particular way. So how do I combine? Well, the thinking is not very sophisticated, but it worked. Well, what if we add them together? That's the simplest possibility. But it's immediately apparent that, let's say the animal has 20 reinforcers for staying and 80 for switching, and another condition is 80 for staying and 20 for switching. In other words, he's getting different at one case switching is favored, the other case staying is favored. They're going to sum to the same thing, but my data tells me the run lengths I obtain are going to be different. So adding can't be the rule. We could multiply them, but again, pretty quickly it becomes apparent that essentially we have the same problem, so multiplying is out. So what about subtracting? Well, that is attractive because order matters, so you're not going to get the same result. But what you are going to get when you've got more switch reinforcers, you're going to get a difference which is negative. And in a very simplistic way, I thought, well, you don't get negative run lengths, so subtracting didn't seem to be a good way to do it. Well, there's only one thing left, and that's dividing. And I was probably very lucky because if you remember the cartoon before, staying was the left lever and switching was the right. And so if I think about stay left, switch right, you end up having to stay divided by the switch. And that's what I did. Had I done it the other way, switch divided by stay, I would have quickly seen that the reciprocal of that would be a neater kind of model. But it just can't work out. Very fortunate that I make the stay lever on the left lever because I'm left-handed. And sometimes when I champion the rights of lefties. So that's why I did that, and so I was lucky. And if you simply think about the ratio, without looking, remember about driving along, but I knew what those figures look like. As the ratio gets larger, one length is getting longer. Well, the ratio gets larger either by increasing the stay uniforces, which is getting to a smaller VR schedule, or by making the denominator smaller. You make the denominator smaller by going to a larger VR schedule, and at least at a conceptual level, it's possible for dividing to be the way you define it. So, all right, so I've got at least one independent variable now to relate to the pi-dependent ratio. What is the functional relation between them? Mathematically, how are they related? And I didn't know. And I had Excel, most people have Excel. And part of what we'll see is there's not a lot of brilliant insight in the development of this model. It's been what I have in front of me and being aware of things and being sensitive to the contingencies of what my data and what the analysis tells me. And Excel easily fits linear, exponential, log, polynomial, and power. Polynomial is really, I knew, inappropriate for this, but beyond that, it seems to me any of these could potentially fit, and none of them could potentially fit, but I thought this is the easiest place to start. And if you're not familiar, this is simply linear data, and I simply have a exponential function and a log function just to kind of show you what they look like. If you take the logarithm on the x-axis, you now have a linear exponential growth function. If you take the logarithm on the y-axis, you have a linear, this is a linear log function, and this becomes a linear exponential growth. And that's, I think, one of the reasons that they were in Excel. You can linearize these to make it easy to fit them. So, turns out with Excel, there are a variety of ways of doing it. And what I want to do is spend a couple of minutes going over, in some sense, the details of this. There's a whole lot of screenshots. As I said, you can download these. But I just want to go through to give you an idea. There's lots of different ways. I don't know that there's necessarily the best ways. I'll try to speak from my perspective what some of the advantages and disadvantages are. The easiest, at least from my perspective, is plotting the data and then using a trend line. So this is just some data. I actually, quite frankly, forget what experiment it's from, but it's for one particular rat. I guess about 9 conditions. And I'm really just going to focus on the response to the reinforcer data. And if you want to make a plot, what you simply do is highlight what you want to plot. It's easiest if you arrange it so that the x-axis is on the left of the data, that's your y-axis. And you simply click on that little symbol up there, and you get this menu. Click on scatter plot, and click no data point, click the data points with no lines. And then you can go next, and you can use some other things. And you eventually get it plotted, and that's what the plot of that data looks like. Normally you have just, I guess, diamonds. I've also highlighted the next thing I want to do. So I can see, simply looking at it, that there's some kind of a linear relationship. It's not a great linear relationship, but it's not an awful one. Next thing I want to do is add a trend line. So within this chart, you go to the chart menu, thing called trend line, and you get this menu on the other side where it says type. You can select either a linear, a log, an exponential. In this case, I already selected linear. And you can display the equation from the fit. You can display the squares, so you can check those two off. And this is what you get. And so that's a reasonable R-square of 0.86. It's funny, I realized after I had done all this, when I'm reading students' dissertations, I always moan at students who carry these out to 6 and 7, 8 decimal places as though that reflects the accuracy of our measurement. And in some sense, I'm chagrined that you're carrying things out to 4 decimal places, and that, in fact, I wanted to do it to show you that all the different ways actually do produce the same result, if it's not any major rounding error, but we really don't. Our measures are not that precise. That's my engineering background coming into this. So, just going to put this here. The particular number is not significant, they're not critical. So when we do the plot within the trend line, we get two things. We can see the data. If we go back, we can take a look at how the data are arranged around that line. And I don't know that I would say they're quite randomly arranged, but there's not a really highly systematic deviation. The deviations could be much worse, let's leave it at that. And ideally, you want to have, when you do any sort of regression, you want your residuals, the differences between the data points and the lines, to be randomly distributed. And that's, for starters, okay. And so you get, when you do the plot of the trend line, you can see visually how the data relate to the regression. You get the values of the slope and the y-intercept, and you get the value of r-squared, how much variance is accounted for. What you don't get is the standard errors of each of these two measures. And you can get some idea, in a very kind of loose sense, what they are by looking at the r-squared. This is reasonably good, so you know the standard errors can be enormous, but you really don't know what they are. So the next thing you can do is there's a regression tool in Excel, and you find that there's on the regular menu that says tools, and you go down to data analysis. Depending upon who installs your Excel program, and sometimes with Fordham when they install it, you have to have something called the data analysis tool pack installed. And they used to not install that because it would take up memory. I don't know why they would do it. But they wouldn't, and so then I'd have to call up the technical people. They'd have to come out and reinstall it. So it turns out if you look and you don't find this, or you see it there, it's, you know how if a menu item is not available, it's not darkened. You need to, if it's your computer, your software, you just need to reload Excel and tell it to install everything. Well, it's call people, but it's not yours. You get it installed. So you click on the data analysis, you get this menu, you find progression. There's an error here. The y-axis is really D, so I didn't realize that I did it correctly, but for some reason it came up today instead of the B column. You simply highlight, you click on this, and you say it's here. Click the X range, you highlight that range. And then finally, you click here, you say where you want the data output. Now you have to click somewhere up here, and then you click OK. You get something that looks like this. Here, in some sense, is a much more complete analysis of regression, but it's missing the graph. So you can see more information about the data quantitatively, but you're missing how, in a visual sense, how the data fits the line. Here's the r-squared, here's the slope, the y-intercept. These are the two standard errors. And it gives you analysis of variance, and it gives you all sorts of other things. So that can be useful at certain times. When I publish something, I always want to include the standard errors. So even though I've done the analysis typically with plotting and the trend line, I review them with this so I can report what the standard errors are. There's another way. There's something in Excel called functions. And functions are that symbol right there. And you simply click on it. And I simply, what I first did is I wrote these things. I want the slope, I want the intercept, I want r-squared. I'll simply give you the example of slope, intercept, and r-squared work essentially the same way. When you click on that, you can click on statistical, so we look at them all and go alphabetically and figure out on slope. And you can click OK. And you get a menu and it asks you to indicate the x variables and the y variables. We plug this in, click OK, you get that as a result. You can do the exact same thing for the y-intercept and for the r-squared. And so this certainly takes up less space on worksheet. And so this might be a way that some people may want to use. Much of what we get displayed here is not useful. And so this, in some purposes, might have its benefit. Notice we're getting the exact same things, and we certainly hope so, because Excel is using the exact same code to do all these things. There's some different ways to get in here. There's another function that we're going to talk about before we get to the solver. And I have to use that solver slide. So we're going to talk about Linus. That's one function that is going to do a whole lot of things in one shot without regression. This is simply, I put this in here so we can tell what is going to be in each of these cells. And you don't have to put this in there. I just did it so I know what things are. And you need to highlight the range of cells that you're going to want this information to go into. Excel is going to use what's called an array function, and that's an array. And you do the same thing, highlight that, then you click a function, you find minus, and you get this menu up here. You click on here, and you take your y-axis, your y's, click on here, and you take your x's. True for constant means you want it to fit the constant. If you say false, it's going to force the constant to be 0, and all your variables will be, the slope will have to count the variables, will do the best job you can. And stats, you can say false. In that case, I forget what it gives you, but it only gives you one value. I think it gives you the slope. If you say true, you're going to get everything out there. So I said true, and click OK. And in one fell swoop, you get the slope, you get the intercept, you get the standard errors of both, getting the variance accounted for. This is the standard error of the estimate supply. This is the F ratio if you care about it, the degrees of freedom. I often like to see the degrees of freedom because it tells me I did it right. I know how many data points I have, and it's a quick and dirty way to check that you actually highlighted the right number of boxes. And if you got to, depending on how you arrange your data, it's very easily to highlight an extra row or an extra column. And, the old computer saying garbage in, garbage out. And so one of the things I'm always telling my students is whenever you work with a computer, I'm always thinking about easy ways I can check to make sure I've done it correctly. And not by estimating, a little, just by paying attention to that or a variety of other things. And then this simply tells us the sums of squares of the progression, and the sums of squares of the residuals. And so that gives more information. The one thing I didn't mention is the peculiar thing about an array function that took me a while to figure out exactly how to do it. After you fill all this in, if you simply hit OK, you simply get one value there. To get the array, get all those filled in, instead of clicking OK, you need to press down Control while you also press down Shift and then press Enter. When you do that, that enters and fills out the whole array and gives you what you need. The solver is an algorithm in itself. It is useful when there is not a way to get an exact fit. It's essentially an automated way for doing iterations. When you do iterations, years ago before there were computers and you could linearize a function and you wanted to fit some data to it, you essentially had to make a guess. Well, I think this parameter is equal to this. I think this parameter is equal to this. Crunch it through on your abacus or your toes or whatever. Come up with a number, see what it looks like, take a look at the R squared, try some other guesses, and keep going and trying to converge at what seems to be your best estimates of those parameters. The solver does it. There are a variety of different Excel calls in the solver. There's a whole variety of different names for this, and it certainly routines and automate the iteration process, and there are some algorithms they have to come up with best initial estimates and best estimates for solving more quickly and so forth. We don't need to go into the details of what they are. And what you need to do for that is you have to get your predicted values. And for your predicted values, you simply are writing a formula. You take the response ratio, whatever your model is. And so this is simply, it's the response ratio times the slope plus the constant. It talks about S, and here we can go there. I don't have on the screen at the moment. What I've now done, this formula actually reads, take the value of the reinforcement, multiply it by the slope of the value here, add to it the value of the y-intercept. So this 1 and 1 are my best guess. That's clearly not a very good guess, but it's the place you have to start. What we also need to put in is the sums of squares progression and the total sums of squares. For the sums of squares progression, there's a function for that, and so we fill those in. For the total sums of squares, there's a function for that, and you simply fill those in. Now you also have to do it with R squared. Now you get to the point where you can use the solver. So you click on Tools and get the solver. Target cell means the cell that you want to focus on. If we're doing these models, typically what we want to do is take the R squared and we want to maximize that. We want to get as much variance accounted for as we can. So I click on that, and then I click on this cell, which fills in the cell name here. And I click that I want it to be maximized. In some other cases, I might want to minimize something, or you may want to have something at a specific value. I think these are probably more interested in reviewing economic kinds of behavioral economics, money economic work. So you've told Excel that you want this value minimized, but you haven't told Excel what to do to minimize that value. And that's what this, by changing cells, is about. You click on that value, and then you click on this cell, then you click on this cell, and you end up with this. And so essentially the solver is going to minimize the value of this cell, which is this one right here. By fiddling around, it's more systematic than fiddling, but by changing these values here, which are these cells up here. And when you click OK, when you click Solve, in about that period of time, this becomes a maximum value. These two values get filled in. These are recalculated as we go along. And the nice thing about solver, this is a linear equation, so you don't need the solver to do it. But if you're working with models that are not linear, or that are more complex, that can be easily handled, even though they're linear by Excel, the solver is a very handy way of doing it. If you use Quantropro has a similar function, whose name I forget. I used to use Quantropro a number of years ago. They have a similar thing there. I just don't recall the name of it. It's handy. It allows you to deal with lots of data sets that are not fitted to functions that can be linearized, or they can be linearized. You can have the exact solution for them. And so, see, there are all these different ways to produce the same outcome. It really doesn't matter which one we use. Now, I've described the data. At least I know how to describe data. I know different ways of using Excel. Now, all right, I still haven't answered my question. What is the relationship between the ratio of the reinforcer state switch and run lengths? And so what I simply did was I fit the data that I had to each of the functions, to a power function, a linear function, a exponential function, a log function. And I used the plot and a trend line because I wanted to see what the residuals were. The R squared is important, but you really have to make sure that the residuals are reasonably randomly, not overly biased towards in the middle on one side and the ends all something of that sort. And of course, as this happens, generally speaking, a power function produced the largest R squared, but not always. It would have made life a little bit easier. The power function, in some sense, always won, but it didn't. I looked at all the graphs, and it was between the residuals and between the R squared, power function seemed to be the best fit. And there was another reason that I ended up selecting the power function. Turns out, and we don't need to do the derivation here, but you can, from the model, if you got that one alternative, the ratio of state switch reinforcers, and then in the current state, you got that ratio of state switch from the other alternative. If you combine those into one equation, as you would if you're doing choice of search, that equation, in fact, can be derived from the generalized matching law, or the other way around, the generalized matching law can be derived from that equation. And so it struck me, certainly the generalized matching law is an enormously robust description of choice, and it struck me as useful, important, maybe not necessary, but close to it. If I'm going to be analyzing the components of a choice procedure, it would seem that from those components I ought to be able to get a description that's compatible with the generalized matching law. And so this power function that I was using can be, we can derive the generalized matching law from it, and so that was the other reason I ended up choosing a power function. So with some of this, there's been considerable luck in a variety of circumstances, but there's also been some logical input. You notice the logic that I've used has not been high-powered logic. This is, if you've got some reasonable comfort with mathematics, and you struggle a little bit, but they self-learn how to do these things. All of this is quite cool. Concurrent performance. Well, I first need to make explicit to you how I really conceptualize concurrent performance. Normally, we think about the choice of left versus right. My conception is the animal really has two sets of choices in a concurrent procedure. You have a left alternative, chooses to stay there or to switch. The right alternative, you choose to stay there or to switch. There are different schedules for these. And my notion is that these two sets of choices are really independent of each other. When he's at the left alternative, it's just staying or switching. The other stuff that happens at the other alternative is in another plane, in another world, in another life. It's not relevant now. There may be some interactions, and that's sort of a bold statement. But at a conceptual level, that's what I assume. So the animal can switch back and forth. So how do I begin to try to test that kind of notion or see the effects of stay and switch schedules? So this is the way to conceptualize when we're talking about the concurrent RI60, RI180 when you talk about stay and switch schedules. At the left lever, it's an RI60 for staying and RI180 for switching to the right. When the animal switches to the right, that RI180, the function of changes to reinforce staying at the right, and the RI60, the function of changes to reinforces switching to the right. And I can run that and have run that and get a very nice concurrent performance that Generalized actually will describe about this. But I wanted to begin to assess some of these factors of staying and switching. So I said, why don't I just take these two switch schedules, exchange them. So instead of RI60, RI180, we'll have an RI60, RI60, and an RI180, RI180. And I can do that with any sort of standard concurrence schedule and just swap the switch schedules. And so I ran an experiment where I had these standard, what I talk about symmetrical arrangements, and then what I talk about here is asymmetrical arrangements. And I'll just quickly go through the model. This is the original model I developed to simply deal with the concurrent, the choice, stay versus switch PR schedules. If you notice, there's an interesting thing here. When the animal's at the left lever, he's going to get on average, earn one reinforcement that is the left lever 0.33 for switching to the right. At the right lever, he will get 0.33 for staying right and 1 for switching left. So the reinforcers earned at these two alternatives are going to be the same. When you get this asymmetrical arrangement, that's no longer the case. Now, when he's at the left lever, 2 reinforcers permanent in the arrangement, whereas when he's at the right alternative, only 0.67 reinforcers permanent in the arrangement. So it seems to me that needs to be incorporated in some way in this model. And I did it a very simple way. You simply take the reinforcers for staying left plus the reinforcers for switching to the right, divided by the number of switches. This model is actually taking the reinforcers at the right, divided by switches, and the reinforcers for switching to the left, divided by switches. They cancel, so you have to see them. And now if we want to get a model for concurrent performance, we take this equation and make the subscripts appropriate to the left alternative, divided by the equation, the subscripts appropriate to the right. Simplify a little bit, and it's that's what you end up with. And I've talked about it as at the alternative model. A number of reviewers and other people have said, why do you like the notion of the stay switch model better? And keeping with my notion at the beginning of the talk to listen to reviewers, I think we're going to have to be switching to the stay switch model. That is something that it makes better conceptual sense to them. That's the important thing, is to try to get people to understand what we're doing. These are the results I got. Filled symbols are the symmetrical conditions, open symbols are the asymmetrical. The line is the fit to the symmetrical, which is essentially standard concurrent procedure. It's pretty clear that the asymmetrical produces a change in behavior that's not accounted for by the same. If you put all the data into the generalized matching law, the fits are not going to be. This is for the lot of responses. This is for the here, this is the, again, for responding. And what I've done is I'm plotting this. The x-axis is my model. And notice that essentially the model makes these slopes equal to equal to it. So that if we have one regression for all 9 or 10 data points, putting them all into the pool at one time, one equation at one time with one set of parameters is going to describe all the data, and that seemed to me to be useful. You could have the generalized matching law fit one set, fit another set, but it's not, since we're always, from the generalized matching law's perspective, always talking about a chain of reinforcers, it just didn't seem inelegant, I guess. This parsimony is what I'm looking for. So I hope there's further evidence or support for this kind of notion. Next experiment, I wanted to have a different kind of manipulation. So what I did here is weight the alternatives. Notice this is a 1 to 3 or 3 to 1, depending which way you want to go back time or the forces. This is the reciprocal of that. Well, this ratio is the same, 3 to 1, 1 to 3. But here, the total number of reinforcers occurring in time is many more than the number that are occurring here. And I ran a few rats on that, and got results that generalized matching law, in some sense what I would expect. The generalized matching law didn't describe it very well. And I then went on to take my model, and I now got really bummed out. Because my model, these data points aren't falling on top of each other. Here it's not too bad. Here they're not on top of it. So I was like, oh man. So I went back. Did I do the formulas correctly? Did I type the right cells? I took the data to the worksheet, copied it all, and redid everything. It was that same thing. I went back to the computer code. I checked the code. It had mislabels. Nothing was mislabeled. So I went back to the computer code, and I played rat. I counted the time. Everything was the way it should be, and this was right. And I was like, oh man, here I am, and where am I, like stuck in water. And I really sat on this for quite a long time. Every 2 or 3 months, I'd go back and, sort of like extinction, you go back and do it again, and nothing works. You just keep doing the same thing over and over. Why would they would change? I don't know, but I didn't know what else to do, and so I was going to do that again. Eventually, it occurred to me that we really have 2 separate things here. And I was interested in one independent variable, so I collapsed them all together with one sensitivity parameter. And I thought, well, maybe if I just departition these, I have this ratio with a sensitivity parameter, this ratio with a sensitivity parameter. Maybe we can get the equation that looks like this. Well, this looks promising, but now I'm back to the problem I had at the very beginning. I've got 2 independent variables, and I've got to fit a model, develop a model with 2 independent variables. How the heck am I going to do that? Well, I said, well, this is the original one. This is a power function. Well, let me give it a shot. Let me just essentially take a power function on both of these. So this ends up plotting as a flat plane. Let me see if that does it. And you can do this with solver. I've got sigma plot, getting with 2 independent variables. Sigma plot can be handy. There's something called table curve, which is like overkill. It'll fit a million functions or something. And it's sort of fun to play with, but you can get lost in it. It has one nice feature. It has a very nice way of displaying the residuals, which it does automatically. And you've got to fiddle around with sigma plot and some other things. And this is what I got. And this, to me, beautifully portrays what's happening. The vertical lines, if you can see them, are the residuals. Here's another one. Virtually 80% of the data points, the residuals are within the data point. So pretty much each of these data points is falling on this plane. I was delighted. This is even better than that sort of part of the pyramid, that first set of graphs I showed you. And so I was really very happy. You can really see here, this weighting biases this is the symmetrical condition of the weighted biases responding in one direction. This was weighted to the other side and had a different, smaller weighting factor. In fact, it was biased that way. And the magnitude of the bias is smaller. Here, with smaller weighting factor bias this way, you always have a bad data point. But everybody thinks that children are beautiful, and I even think that bad data point is beautiful. And I was willing to go with that. If you look at the, now what we need to do is the generalized matching plots. This is just a reminder of what those look like. This is the data that we saw earlier. And this is what they look like with the old model, and this is what they look like with the new model. So they, the model with a power function, double power function, if you will, not only fits the weighted data, but also fits the asymmetrical data, and I was really quite delighted with that. So, plotting data is critical. You can see what's going on, particularly if you have the right model, which is really very illuminating. I was lucky that it was a power function. I didn't have to continue my search. My problems aren't yet over. I would go on to those other problems, but I know my time's up. And essentially, it's getting some data to account for when there's just one state switch arrangement. There's some funny things that go along with the model. Some conclusions. You need to be thick-skinned. Not that people say uncontinuously, but you need to. One of the wonderful things about JF reviews is even when you get rejected, they do it with a smile, and they do it with a very helpful, positive smile. They tell you they're enormously informative. And although there are certain respondents that are elicited when you get rejection or revise and resubmit, over time those respondents extinguish, and you sometimes need to let them extinguish before you read the letters. You've got to be persistent. It's both in terms of trying to understand your data, in terms of submitting manuscripts. One of the biggest problems I had in the first few manuscripts I was submitting is I didn't know it at the time, but I didn't really understand what my data were doing. I knew mechanically, I knew I could fill with these schedules and produce certain outcomes, but I didn't have a conception of what was going on. And that was essentially, I think, the main problem. Once I really came up with a conceptual understanding, at least I have at the moment, it seems to have been much easier to get things accepted for publication. And you've got to have that persistence. I may be funded on a grant, and I've been 7 iterations. I was talking with the program officer. He said, "You're very persistent." And I said, "Yes." And this is one of the things to the NIH reviewers. Even when I got rejected, there was a kernel who said, "Gee, this is a really interesting idea," and everything else that he produced said, "But you're not presenting it in a way that allows us to give you some funding." And so, if they hadn't said, essentially, there's something very interesting here, I said, "Well, throw it away. It's a lousy idea." But that kept me going, and so thank you if you happen to be in the room. I think an important feature is to identify the contingencies. That's essentially, I think, one of the important things, and I didn't even identify. Larry Carl told me that. I gave a talk about this a number of years ago at a conference, and I didn't quite have it conceptualized as I do now, but I gave the talk and got some questions, and afterwards went down to the bar, and Peter Colleen was there, and he was sitting there, and I walked in, he said, "Hi," and he looks at me and smiles, and said, "So it's all just the contingencies?" And I said, "Yes," and it was like, it was so deflating because it took so much work to think about it and so forth, and then Peter just blew it off, and it's just the contingencies. It's like, oh man. Well, a couple years later, I was at Alabama, and we happened to be at a bar, and I said, a long time ago, he said, again, it probably speaks more about my misinterpretation of certain kinds of messages. For him, saying it's just the contingencies is to really say, it is just the contingencies, and the magic is identifying the contingencies and identifying how the contingencies operate. And so I would say, I think there were a number of presentations, for example, of SQAB, problems people were addressing, where the contingencies haven't been identified. I don't know what the contingencies are, but as looking at it, I knew what they did, but I didn't know what the contingencies really were. And so, if you're interested in starting, if there's a problem, are the contingencies clear? Have the contingencies actually been identified? In concurrence, we always knew that the gamma switches. We always knew that they were reinforced. That's why we put in a changeover delay. We never really thought about what the contingencies were. And so I think that is an important thing to do. Listen to other people. Whether it's reviewers, grants, manuscripts, when you present, or when you post your not everybody's comment is worthwhile. But you'd be surprised, sometimes I think it's an unworthwhile comment, and the unworthwhile comment really reflects my lack of understanding of what they were trying to say. Listening is key, and you can learn a lot. And it's to find things throughout your day. I mean, this is what science is about, is to find order in the world. And there are lots of different ways of doing it. I'm not trying to say that my little story is the way to think about science and the way to conduct quantitative analysis. But I was really trying to present that you can get into some, I think, pretty interesting areas, and at least from my perspective, get some interesting results. Now, I started this in 1992, and here it is 2007, so it's been 15 years. It's been a long road. For a long time until I get it first been published. And that was it took me a long time to conceptualize what it was I was doing, and so you need to be persistent. Thank you very much.